Hello, everybody. Today we're going to continue our talk about Chapter 15, active filters, and I want to start by just doing a little bit of review. We did last week the two-pole, or right before spring break, the two-pole low-pass Butterworth design, and the schematic shown here is is a two-pole. It shows the two capacitors and two resistor pairs. And notice R1 and R2 determines the damping factor, if you remember that. And there's a table that we use to a Bessel function table, which determines the damping factor based on those resistors. The 1 over 2 pi RC formula determines the cutoff frequency. So these capacitors and resistors here determine the cutoff frequency, and then R1 and R2 determine the damping factor, which determines the filter characteristic, whether it's Butterworth or Bessel or Chevy-Chev and so on. Today what we're going to do is we're going to do a 4-pole Butterworth filter, and we're also going to look at a Bessel filter. Okay, so remember last week, the last lecture, what we did is we determined the cutoff frequency resistor, and the resistor value and capacitor value of 22K and 4.8 nanofarad for 1.5 kilohertz cutoff frequency. So you work this 1 over 2 pi RC formula for that. Choose R as 22K, and then you solve for C at 4.8 nanofarad. So the standard value is 4.7 nanofarad. So we put those in there. For the Butterworth filter, this is a Butterworth filter values. This is the Bessel table for Butterworth filter. There's different tables for different filter characteristics. This is the one for the Butterworth filter. I wanted to point something out here before we move on, because we're going to do a 4-pole filter in a minute. I don't want to have to come back to this table. You see we have this 0.586. We did this last time. So that's what the ratio of R1 to R2 is going to be for a 4-pole filter. All right. I'm sorry, for a 2-pole filter, a 0.586 for a 2-pole filter. Okay. For a 4-pole filter, we're adding a second stage. So we're going to have to use these numbers, okay, and these numbers. So we'll look at those when we do the example, and we're going to use, for that, we're going to use 0.152 for the first stage, all right, and 1.235 for the second stage. So just remember that, okay? But for now, we're at 0.586 for our 2-pole, which is minus 40 dB per decade for 2 poles. Remember, it's 20 dB per decade per pole. So 2 poles is 40 dB. When we do that 4 poles, we're going to go to 80 dB, which would be 4 times 20. So we choose resistors closest practical to the desired ratio, 33K and 56K. Now, 1% precision resistors, you can probably find resistor values that are a little closer than just 33K and 56K. And there are online resources where you can actually, online calculators where you can calculate those ratios much more accurately. Okay, so here's our 33K and our 56K, and this is sort of where we left off last week. This demonstrates the Bode plot for the multi-sim simulator with a full circuit. Okay, so you get that 40 dB per decade roll off. The actual frequency, cutoff frequency 1.547. So what do we do to do it from change a 2-pole to a 4-pole design? Well, you can always just bolt on another exact same circuit. Okay, we have a 2-pole Butterworth filter here. Putting another one right on back of it, you get a 4-pole. Now remember, for the passive filters, which were just RC, no op amp, if you could do that too, it would be a 4-pole filter, going from 2-pole to 4-pole. The problem is you get all that loss through the resistors, and your output impedance suffers, okay? With this, it doesn't suffer at all. You get just the same low output impedance from your op amp, so you don't get any compromise at all of your performance. Your input impedance stays the same, your output impedance stays the same. It actually is much, much better than the passive filter. So what we have to do now, all of these values here, these cutoff frequency resistors and capacitors are all the same, 4.7 and 22K, right? But we have to recalculate the R1 and R2 and R3 and R4 based on that table for the 4-pole design. So the resistor ratio for the first section is 0.152. Remember that from the table. And then the second one is 1.235, resulting in a gain respectively of 1.152 and 2.235. And so they've chosen some standard values here for that. So that's a 4-pole filter. Really nice filter. This would work very, very well for a lot of good applications. 80 dB per decade drop after the cutoff frequency. So that's low pass. We know it's low pass for one reason. We got this capacitor to ground, so that's going to short all the high frequencies to ground. And this does similar thing. This bypasses all of the gain. This capacitor up here along with this one. But how do you change it to a high pass filter? Well, it's really simple, believe it or not. What you can do, this is again the low pass version, is swap the positions of the resistors and capacitors. Now, these resistors stay the same. The damping factor resistors, they stay. They don't go anywhere. But all these capacitors and resistors change position. So let's see if we can show that to you right there. So that resistor, RA1, was a capacitor before. That was CA1. Now that CA1 is now a capacitor. It used to be a resistor, and so on. Same with these two. And it'll have the exact same performance as the low pass filter, only now it's high pass. Okay, so instead of getting a roll off at a high frequency, it'll get a roll off at a low frequency. Okay, pretty simple, right? Now we talk about Bessel filters. Remember the Bessel filters are what? Linear phase. That might be on the exam. Linear phase. That's the important thing. So no matter what frequency you're at, the phase response between the phase relationship between the input and output are identical. It doesn't matter. Let's say you have 80 degrees phase difference between input and output at 1 kilohertz. Well, you go to 10 kilohertz, still going to be 80 degrees. 100 kilohertz, still 80 degrees. That's a big deal mostly for pulsed waveforms. Okay. So here's the same table. I mean, not same table. It's a different table, but it's similar, where you have the order of the filter. Here we have a second order filter, 2-pole or a 4-pole filter. And we have the ratio of R1 and R2 with a first stage or second stage. Okay. So here's R1 and R2 for the second stage, and that's R1 and R2 for the first stage. If you have a 4-pole filter, if you have a single pole filter, then all it is 0.268 in this case for R1 over R2. Same filter, circuit, very similar. It looks the same, right? Watch. All you do is change your resistor values over here, R3 and R4 and R1 and R2, to correspond to the ratios in that Bessel table, the Bessel filter table, instead of the Butterworth filter table. Okay, actually they're both called Bessel function tables, unfortunately, but one has Butterworth values in it, the other one has Bessel filter values. A little confusing, but so anyway, here we are. These capacitors and resistors are always the same, right? They're the cutoff frequency resistors and capacitors, 1 over 2 pi RC. Those capacitors are the same value, resistors the same value. This is the damping factor resistors. This one on these on the output, 3 and 4, R1 and R2. And so you go back to that table here, this table, and R1 and R2 are going to equal 0.084 in the first stage, and the ratio of R1 divided by R2 is going to be 0.759 in the the second one. So right here, so this is going to be 0.759. Okay? Now you'll be able to use those tables on the midterm. Next midterm coming up in a couple of weeks, or I guess it's, yeah, a couple of weeks. So, or they'll be included on the exam itself. So one of the two. You won't have to calculate anything. It's just look it up, basically. Well, you have to calculate the ratios, but you just have to look it up on those tables. Okay, so that's all for this week. It's a short one, but I want this stuff to sink in pretty good. There's a lot of good exercises in the textbook. We have one more week of chapter 15, which will look at some other filter topologies. And I hope everybody had a safe and fun spring break. See you next time.